Sunshield.
Liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. We do have confirmation of observatory separation. The James Webb Space Telescope amidst applause here in the Mission Control Center. And there is the view from the upper stage camera on the Ariane 5 looking at the James Webb Space Telescope as it moves gently away from its launch vehicle.
Go away.
Yes, go away.
Ironically enough, as we marvel on this view from the upper stage camera, this will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth. Quite a Christmas present for the world's astronomers as the James Webb Space Telescope begins its life heading towards deep space.
After yesterday's successful completion, Webb Sunshield deployment, mission controllers at the Space Telescope Science Institute in Baltimore, Maryland, are today ready to move on to the next major spacecraft milestone, the deployment of Webb's secondary mirror. In just a few minutes, the team will send a signal to release Webb's secondary mirror support system. Today's activities mark the first in a series of deployments related to Webb's optics. Those beautiful golden mirrors
are fully tensioned.
How exciting.
Simply, significant milestone accomplished. Job well done, Sunshield team. Job well done.
Thank you, Mom. That is on the window. Please check on the spacecraft vessel.
And OC, that looks good. You're go to execute.
Copy.
I'm your host, Michelle Thaller, and for the rest of this remarkable live stream, we'll be dialed into the action as mission managers proceed with setting up the Webb Observatory on its way to a parking orbit 1 million miles away from Earth. Joining me to share information and insights into this process is Julie Van Kampen, the Deputy Commissioning Manager for James Webb. So welcome, Julie.
Thank you. Thank you for having me. Thank you, Michelle.
So as we listen for confirmation of the secondary mirror support structure release, let me talk a little bit about how things are going to work today. We're looking live at the MOC, the Mission Operations Center at the Space Telescope Science Institute at the campus of Johns Hopkins in Baltimore, Maryland.
Step 020.
And you'll notice that we are occasionally pausing to listen, and that's because we are actually pausing to listen for the live updates from the MOC about the secondary mirror deployment. So as we are conversing, if you see us pause, we're both kind of wondering what's happening next. We're listening for the command because you are actually live with us today for this incredible secondary mirror deployment. So so Julie, as we listen for confirmation of the secondary mirror support structure release, how are things looking today? How are things going?
Things are going really well today. Things have worked incredibly well over the past 12 days. We've had moments of excitement and lots of tension as we kind of wait to see how things work out. But overall, great. We're right on or slightly ahead of schedule. It's from the moment where Arianespace was able to put us right where we needed to in orbit. It's been going great.
So what is the first step in today's deployment? And this involves something called NEAs. These are non-explosive actuators. When is the team going to start that?
They should start that soon. Right now, they're in the middle of checking out to make sure that the 2 motors that they use when they do the deployments are working. They do an aliveness check. They make sure everything's ready to go for it before they release the launch locks. And then once they release the launch locks, they'll do a small move of the secondary support structure to bring it out a little bit more than a degree. check out all their telemetry, make sure that they're happy with how it's performing before they complete the full move. Then there's a sequence that they'll go through to lock the mechanism into position, where it's at the right orientation to have the mirror captured into the observatory's wavefront sensing system, and so that it can be aligned later on.
Absolutely. So as our viewers are tuning in right now, let's sort of go over what's happening to on the screen in front of them. So as we mentioned, we see some windows into the MOC, the Mission Operations Center, and that's as we said before, on the Johns Hopkins campus, Baltimore, Maryland. And then on the left side of your screen, you're seeing an animation, but this isn't just any random animation. This is actually based on real data. So Julie, could you tell us a bit about what we're looking at as far as this animation here?
Sure. This is called our Observatory Verify visualization tool, and it's a really interesting work between 3D modeling and some telemetry coming directly from the spacecraft. And you'll be able to see this as we go through, that there's some real-time telemetry being fed into a model, which then reacts as though the observatory is actually doing those movements in space. It's not a video or a model that's pre-programmed to do that. It's actually receiving the telemetry and can model to match that telemetry.
We are go to stop the DU motor.
So they're stopping the motor, they're doing their aliveness check.
And OC, you have a go.
Copy, go to continue.
So Julie, you were saying to me, oh, go ahead, please.
I was going to say, you hear them talking to each other in the control room. Each person has different call signals. So you'll hear one person called OC, that's the operation controller, and you'll hear CC, that's the command controller. And the two of them work together to make sure that all the commands that are sent up to the observatory are exactly what we want to do and configured properly.
And I verify that command queue is in the central window.
Copy.
So OC, at this time, we are going to proceed on to step 022 to disable the ADU critical command.
Copy, that's on the window.
And OC, that looks good. You're going to execute.
Copy that, executing.
And OC, you have a go to continue.
Copy, go to continue.
So Julie, can you talk a bit about the important thing that's happening today is the deployment of the secondary mirror, and give us a little sense about what this is. Oh, and feel free to listen to the calls. I know that you're doing this live with us as well.
Copies. And OC, I have also confirmed with the data lead that we are ready to perform the SMSS latch motor aliveness. So at this time, we are going to proceed on to step 024.
So they just talked about the latch motor aliveness. So before they were checking the deployment motor, and now they're going to check the latch motor, because they have two different motors that have to operate during the sequence.
And
the secondary mirror itself, to talk about that for a moment, if you take a look at the visualization tool right now, you'll see that the mirror does not look very functional if you want it. It's broken into pieces. The two wings are folded back on the sides. And the secondary mirror is those two black lines going up to the top of the mirror. And it's a little hard to see, but the mirror itself is actually perched on top of the telescope on those two long spindly legs. What will happen is it will fold out and it will put it down into the center of the primary mirror, where it can be reflecting light back into the center of the telescope. The telescope itself is a reflective telescope. It's a 3-mirror anti-stigmat. So the light, we'll talk about a little bit later about the light path, and you'll see once it comes out that it's right on the center of the telescope on 3 long spindly legs.
Standing by.
Julie, I understand we have an animation that we can play now about the secondary mirror and sort of how it will fold out. So here we go. If you can just tell us what's going on here.
Yep. So you can see the legs come out, and the top leg has a hinge in the middle of it, and it snaps into place. And we're seeing the back of the mirror, so it looks black, but that round item in the center is the mirror, and you can see it's held a certain distance away from the primary mirror. The primary mirror is concave, and the secondary mirror is convex, and it shoots the beam of light back down through the center of the telescope.
Those parameters look good. We are go to continue with the motor.
Instruments are packed into a box. You can kind of see behind the telescope. There's a rectangular box with a sloped top to it. That's where all the instruments are packed back there, and they take the light in from the center of the telescope and bring it down onto detectors for us.
And OC, we do expect the yellow alarm for the motor arm.
So they're talking about alarms right now on the loops, and what they mean by that is as we move through different checkouts, there's telemetry that comes into the mock, and it gets processed into a ground system, and that ground system looks at the telemetry, and it has different parameters set up. And to alert us when things are happening, we've assigned essentially colored lights to come on. It's on your digital screen. They're not light bulbs. So an alarm will come on someone's screen and say that this motor is doing something, or this temperature sensor is doing something. And some of them are meant to be in that state during different times, and some of them are not. So we watch them and we alert each other to our plan as to what we should be seeing at what time.
For those of you who are just joining us, we are looking at live coverage of the deployment of the secondary mirror for the James Webb Space Telescope. You're looking at an animation that includes real-time telemetry, real-time data from the spacecraft as to the configuration that it's in and what's going on.
Complete. Stand by for evaluation.
And you're listening to live commands coming from the Mission Operations Center, or MOC, at the Space Telescope Science Institute in Baltimore, Maryland.
OC, DevOps on Ops. We have verified that the sync move was good, and we are go to proceed with the launch lock releases for the SMSS. At this time, we are go to proceed on to step 026 for all channels safe verify.
Copy, copy.
And we have an expert with us.
In the window.
Yes, please go ahead.
OC, that command line looks good. You are good to execute.
Copy.
At this point, they're getting ready to release the launch locks.
And OC, you're go to continue.
Copy, go to continue.
We're going to hold here and listen to the commands. This is a very momentous event happening. The extension, getting ready to extend the secondary mirror. You're watching live coverage of this. We'll hold here just for a little while, and we're going to listen to commands from the MOC. As we listen for more commands from the MOC, one thing I'll add is that we will have time, we believe, to take some questions from social media. Use the hashtag AskNASA. We will get to as many of those as we can. We're on multiple platforms, wherever you are, hashtag AskNASA.
Complete.
DevOps copies, and I can confirm all channels are safe. So at this time, we are going to proceed on to step 027 for the OTE LRM Group 3. And OC, that script looks good. You're go to execute.
Roger, executing.
And OC, you are go to continue and enable ordnance cards.
Copy, go to continue.
OC, I can confirm both ordnance cards are enabled. You are go to continue with ordnance channel arms.
Copy, go to continue.
And OC,
Julie.
I can confirm both ordnance channels are armed and the SCS is enabled. All stations, the next command will fire OTE LRM Group 3. OC, you are go to fire.
Copy, go to fire.
So
And Julie,
they're
if you can give us
firing
any commentary, yes. Thank you.
Yeah, they're firing the launch release mechanisms for the optical telescope elements. That's the OTE LRM that they're talking about. And what these are the pins essentially in a holder that restrain the mechanism during launch to make sure that, during the forces and vibration that we see, that everything stays in position and doesn't put undue strain onto the motors or the mechanisms themselves during that launch. And at this point, we're releasing them so that we can then move the mechanisms.
So first, we're going to release the mechanisms that keep this all in place. And then when can we expect the secondary arm to actually begin to move?
Well, it will. The very first move will be extremely small. So I am not sure that we will be able to discern it on the visualization tool. But definitely once we get into the full move, we will be able to see that. Once they release those mechanisms, they'll want to take a moment and check out and make sure that everything is exactly what they want before they move on.
And OC, I verify proc complete. So at this time, we are going to proceed on to step 028 to release the OTE LRM Group 5. And OC,
and
that script looks good. You are go to execute.
Roger,
and here's the
executing.
next launch release
and
being
OC, you are
released.
go to continue and enable ordnance cards.
Copy, go to continue.
And at this time, what they're doing is they're running scripts that are made and tested well in advance. They're tested on simulators. They're tested onto the real hardware when we're doing ground test. And they've gone through these scripts that send up commands to the spacecraft.
I can confirm both ordnance cards are enabled. So you are go to continue with ordnance channel arms.
Copy, go to continue.
And as we walk through the script very carefully with the deployments lead and the operation controller, they, as you can hear, talk back and forth and very slowly walk through the script in the step and allowing the commands to be sent up to the spacecraft as we move through it. Some things are checked automatically by the script, and some things we wait for verification from the engineers on the ground before moving on.
OC, I can confirm both ordnance channels are armed and the SCS is enabled. All stations, the next command will fire OTE LRM Group 5. OC, you are go to fire.
Copy, go to fire.
You're watching live coverage of the deployment of the secondary mirror, an absolutely essential component of the James Webb Space Telescope. We are getting ready to extend secondary mirror in a few minutes from now.
And when they say go to fire, what they're actually doing is they're putting a current through a break wire that releases a coiled wire that lets a cone and cup assembly loosen and separate.
You'll hear commentary from myself, Michelle Faller. I come to you from Goddard Space Flight Center.
And OC, I can verify plot complete. At this time, we are going to execute 029 to configure the DEU to standby mode. And OC, that input looks good. You are go to execute.
Copy, executing.
And what they're doing
OC,
now
you're
is
go to
just
continue.
Copy, go to
putting
continue.
the motor into standby while they get ready to do the next steps of the deployments.
And of course, the reason this is so dramatic, you're looking at something very historic here. This is the largest space observatory ever launched, the James Webb Space Telescope. And the mirror assembly is so large it had to be folded up. People often say like origami to fit into the rocket. We'll talk more about that later when we have some time as they're verifying the secondary mirror
OC,
deployment
I
and also
verified plot
latching.
complete, and I can confirm the DEU is in standby mode. So at this time, we are going to proceed on to step 030 to execute the SAP parameter upload.
Copy that. That is on the window.
And OC, that looks good. You are going to execute.
Executing.
You're hearing commands from the Mission Operations Center, the MOC.
And OC, you are go to continue.
Copy, go to continue.
Yesterday saw the tremendous success of the deployment of the giant heat shield to keep this a very cold, infrared, heat-sensitive telescope. There's a gigantic 5-layered heat shield. Each layer is about the size of a tennis court. And yesterday we were with you live for the finale of that, as the final layer was deployed and tensioned, pulled tight. It is now fully functional, fully operational, cooling the telescope as we speak. The telescope components, the mirror will always be pointed away from the sun, and as such, exposed to the cold vacuum of space, will cool to temperatures close to minus 400 degrees Fahrenheit. And that has begun because the heat shield is already
Ops, this
doing
is
that.
Mom on Ops.
Is DevOps, go ahead.
Yeah, it's just looking for you to confirm you've gotten joy this far with all your expectations.
That's affirmative. We have been proceeding as expected.
Copy that. Thank you. Some of the telemetry we see in the flight control room is different, so we didn't know what you guys were all looking at, but that's good to hear. Thank you.
Copy, copy.
And that was the voice of our mission operations manager as he was talking to the deployment team. His acronym, obviously, is MOM. So you'll hear people call it to MOM, and sometimes that's a little surprising. But it stands for Mission Operations Manager.
And Julie, you are the deputy commissioning engineer, and also you were the lead systems engineer for the instrument package, I believe. Maybe just give us a little introduction again as to who you are and your role on this mission.
Sure. So for commissioning, it's breaking down into several parts. Like the parts that we've done over the last 12 days is really focused on some of the spacecraft deployments, getting the solar array out, getting the communication system up and working, getting the sun shield out and tensioned. And it's all been very, a lot of intensive work on this team that built the spacecraft and the sun shield. And then today kind of marks a transition point. So today we switch gears and we work more onto the cold side, onto the optics and the optical telescope element, and getting that deployed and set up for optics. And then the final part of commissioning will be, we switch gears again. We'll go into the science instruments and getting them turned on and calibrated. So as our commissioning is broken into these different segments, we have different people who kind of oversee from a technical point what's going on and how things are going. So my expertise is more towards the telescope itself and the instruments, and then there's other people who have overseen up to this point. And a little bit today, I want to give a quick shout out for the people who built the telescope and assembled it and done it. I wasn't directly involved with a lot of that, but as you can see, all those people are needed to be there in the control room, watching the data, be available if there's problems or questions. So I get to fill in today for the telescope and to talk about this. And you'll probably hear from some more people along the way, Michelle, as different experts have more time and availability to talk to you.
Well, we're certainly happy to have you here, Julie. We're looking at live coverage of the deployment of the secondary mirror for the James Webb Space Telescope that should be happening in a few minutes from now. We're looking at a real-time animation created by telemetry, that is data from the telescope. And then the other two windows are live views of the Mission Operations Center.
And as they get ready here, I can watch my screen and see what step they're on. They're moving forward through their timeline, and they're getting ready to do a couple of setup steps with their motors, and then they'll be moving on to doing their small mirror move to make sure that the deployment motor just a few degrees, actually 1.3 degrees out, to make sure that everything looks good before they do the full deployment.
As we're talking, you'll occasionally see us pause as we listen to commands from the Mission Operations Center. But whenever we have a few minutes to fill some time, Julie, one of the things that we talked about before was the fact that there are no actual cameras for us to see on Webb what the telescope is doing, and that was something that was a deliberate decision. It was definitely thought about, but there are several things that make this very difficult to have cameras on this particular mission. I don't know if you'd like to go through some of that. I remember some of the reasons myself.
Yeah, sure. We would, in this day and age, everything's caught on camera. But realize that James Webb has been designed over many, many years. We did look at the possibility of adding some cameras that would give us some views similar to this visualization tool. However, the thing that the tool can do for us is, as you see right now, the mirrors are bright and shiny as though there's light shining on it. But the reality is, out in space, it's dark. It would be like walking into a dark room and looking at the telescope. It would be dark. So we would need some kind of light system on a camera system. We would have problems if we wanted to do flash photography. Obviously, our mirror is very sensitive, our optics inside are very sensitive, and most importantly, our detectors all the way deep inside of our instruments. We even looked at how sensitive they are to simply lights in the room. If your fluorescent bulbs in the clean room over years would degrade our detectors, we certainly don't want to be flashing them with a flash for a camera The other thing is that, as you can see in our Where's Web Now tool, that we're getting colder and colder. So a camera that you would get that would work at those temperatures would have to be specially designed. You know, plastics fall apart and they shrink and can crack. Glues don't hold together. I mean, to make something that would work at the cryogenic temperatures on the cold side of the sun shield would take a lot of engineering and design. And then one other major issue is that we would have to run cables and power out to these cameras, and our power balance, especially on the cold side of the telescope, is so delicate. Those would be essentially heat leaks, and we would not want to pick up the signature from those cables into the telescope optics itself and take a risk of...
And OC, I can verify prop complete and all loads executed successfully. At this time, we are going to proceed onto step 0 through 1 to configure the DEU to operate frame 14.
So we would not want those
And OC,
cameras
that
to
looks good. You're
interfere
going to execute.
optically,
And
or
OC, you are going to continue.
or thermally.
Feel free to pause, Julie. We can come back. That's right. Yes.
And last of all, if the camera did fail, we would certainly not want the debris from the camera to be moving around our telescope. There's also two sides of the telescope. This is the side we're working on today, but for the earlier deployments, we would have had cameras preferably on the hot side. But as you can see, maybe in the video where the observatory is moving away from the upper stage of the rocket, we're very shiny. So
And OC, I can verify prop complete, and the DEU is in operate mode frame 14. Stand by for depth lead verification.
Copy. Standing by.
And to have a camera to do anything useful with that bright of a background would be very difficult too. It's a little bit of a hall of mirrors with the shiny surfaces. What would you look at to be able to distinguish what's going on? So from an engineering perspective, we decided that our telemetry coming down was the most reliable thing that we have. But when we did see the solar array deploy it from the camera from the upper stage, that was really quite exciting for us.
Yeah, this was amazing. So what you're looking at here on the screen is the actual footage of the observatory leaving the Ariane 5 rocket. You see the logo of the European Space Agency. They were the providers of the Ariane 5. And as the James Webb Space Telescope they're flying off independently into space. Our last view of it, one of the things we were able to see is the solar array deploying, and so that was amazing. I was not expecting that, and there were so many cheers and so many smiles as we saw that heading off into space. Webb is going about 1 million miles away. It is going to a Lagrange point. That is a point where the gravity of the Earth and the sun and the moon balance. It's a great place to actually to park a spacecraft. Everything kind of balances and keeps there. The solar array that you see deploying right now, if you look over at Webb going off into space, you see the solar array deploying. That was the first of its deployments that allowed the spacecraft to power itself up. And we are now very, very much involved in the rest of the deployments. Yesterday, we had the incredible finale of the giant sunscreen successfully deploying. And today we are looking for the secondary mirror, the focusing mirror, to deploy. There will be deployments and commissioning for quite a while. The major ones will be completed all about 29 days after launch. Nice little dramatic lens flare there from the sunlight hitting the back of the James Webb Space Telescope as it goes off into space.
So Michelle, as I listen to what's going on here, they're in the process of doing their small move, which, like I said, I don't believe we'll be able to detect on the visualization tool. But they're waiting for confirmation from the deployment lead that the move is stopped.
So at this point, all of the latching mechanisms have been released, so that the mirror has actually been released, and now we're waiting for a small move, to check and see that everything's all right, and then later on in the broadcast, the deployment of the secondary mirror, and we will be with you through the deployment, and then also through the latching, as the secondary mirror is latched solidly into place, and we know that the secondary mirror has been successfully deployed. We expect the latching to take place. Julie, correct me if I'm wrong, but I believe that will be about 45 minutes after the deployment of the mirror. Is that process will be complete?
Yes. Yeah, the latching has a couple of steps. They move through it slowly. They want to make sure that everything's in its precise position, so that once it's latched, it's completely. We do not come back and ever adjust this again. Oh, they must have gotten confirmation that the small move was successful. I see celebration.
What you're looking at is live footage. This is happening right now at the MOC, the Mission Operations Center. You're looking at the deployment of the secondary mirror of the James Webb Space Telescope, an absolutely essential component.
OC, DevOps on Ops.
This is Sophie. Go ahead.
Step lead has confirmed we have positive separation, so we are go to proceed onto step 037 to stop the DU motor.
Copy that. That is on the window.
And OC, that looks good. You're go to execute.
Copy, execute.
And OC, you are go to continue.
Copy, go to continue.
You can just hear the excitement in the voices of the people on the floor as they're announcing the success of this first small move, because this is, once this small move is seen to be successful.
Complete.
DevOps copies, and I can confirm the DU motor has stopped. So at this time, we are go to proceed onto step 038 to configure the DEU to standby mode.
Copy that. That's on the window.
And OC, the command line looks good. You're go to execute.
Copy, executing.
And OC, you are go to continue.
Copy, go to continue.
So now they'll go ahead and get ready to do the full deployment. But the small move gave them so much confidence in the motor doing its job, and the mechanisms working and moving, just as expected. So they're coming into this next major deployment with a lot of confidence.
As we were saying, there are no live cameras on the Webb telescope
OC,
for many good reasons.
Confirm bot complete, and the DEU is in standby mode. So at this time, we are going to proceed onto step 039 for the integral gain SAT parameter update.
OC copy, just on the window, please concur.
And OC, that looks good. You are going to execute.
Copy, executing.
And OC, you are going to continue.
Copy, go to continue.
What you're looking at on the left-hand side of your screen is the observatory visualization tool. And actually, we have a question from social media. There is a devil on Twitch that says, will this observatory visualization tool be made available to the public? And Julie, I believe this is something people can follow along with on some of the websites. Is that correct?
I think people are putting out information on the website, and I think you can get different updates, but I don't think the tool itself is available.
Right.
If that's what they're asking.
Right. You can go to the website Where is Webb, and there's lots of information as to where exactly Webb is on its path out to L2, the Lagrange point, 1 million miles away from Earth, as well as the temperature. You can actually see in real time the different temperatures on the sun side of the telescope and the cool side of the telescope. And we were talking about the sensitivity. Please go ahead, Julie.
we were talking about the different temperatures on the cold side of the sun shield here. And even in our visualization tool here, you can kind of get an idea. Anything that's down close to that sun shield is going to run a little bit warmer because there is some heat that comes through. There is some heat that gets reflected up into it. There's essentially a hole through the center of the sun shield that has all of the structure and cable running down to the hot side of the spacecraft.
DevOps copies, and I can confirm the load was executed successfully. So at this time, we are going to proceed on to step 040 to configure the DEU to operate frame 14. And OC, that command line looks good. We are go to execute.
They're getting ready. They're getting ready
And
to
OC,
do
you
the
have a
full
go to continue.
here.
Copy, go to continue.
We were talking about the temperatures of the items closer to the sun shield being warmer than the stuff away from the sun shield. And as you can see, the secondary mirror itself being perched on top of the telescope at the moment is one of our colder items. Even when it gets deployed out. Yeah, oh, there's a great picture. You can see that the secondary mirror here is at the top of your screen on the dark side, on the cold side. And it does run, it does not have its own radiator, but it runs very cold. It's one of the colder items on that side. And the sun shield itself is basically what keeps it cold, and the fact that it really doesn't generate any heat itself. Here we
When
go.
you think about the temp, here we go.
Yeah,
OC, DevOps on ops.
This is Sophie, go ahead.
Dep lead has confirmed we are ready to proceed with the SMSS deploy. So at this time, we are going to proceed on to step 042 for the SMSS motor move.
Copy.
You're looking at live coverage of the deployment of the secondary mirror, an essential component for the James
And
Webb
OC,
Space
that
Telescope.
command line looks good. You are go to execute.
Copy, go to execute.
And OC, you are go to continue.
Roger, go to continue.
And OC, stand by for verification.
Standing by.
Julie, can you tell us what SMSS means, the acronym that we're hearing?
Sure,
And OC,
that's
DevOps
secondary
on
mirror.
ops. Those parameters look good. We are go to move the SMSS motor.
Roger, go to move.
That's the secondary mirror support structure, and it's a 4-bar linkage. You'll see it kind of unfold here. Kind of almost looks a little like from a high-tech movie, but it will move in a linkage assembly
Motor status
out
goes
until the joint in the middle of the top
Copy.
leg locks into position. So there's hinges at the bottom, and there's a hinge at the mirror on the short leg, and then there's a hinge in the center of the shorter leg, and then a hinge at the top, very top of the mirror. And the two short legs fold into one long leg.
One coming attraction for this broadcast is that once they extend the secondary mirror, there'll be about a 45-minute period where they latch the mirror, where they make sure that it's very strongly and solidly put together. And during that 45 minutes, we'll be able to show you some footage of the actual testing and building of the secondary mirror. It's surprisingly large. Those booms that are extending from it. Julie, you may know this offhand, and if you don't, when the booms are extended, about how far away is the secondary mirror from the primary mirror?
Oh, I should have looked that up. No, I don't know.
Yeah,
off the
well,
top of my head.
yeah. One of the privileges I had working at Goddard Space Flight Center was watching tests like this, and I did see the secondary mirror deployed, and it was to me it seemed like it was perhaps nearly 2 stories away from the primary mirror, and it's a spectacular thing to see, and like I said, after we have confirmation that this event is concluded, we will then be latching. We'll have about 45 minutes to talk more about
And
this.
OC, DevOps on ops. This motor move takes about 11 minutes, and we'll give periodic updates.
Roger, that.
Yeah, so
Standing by.
here you can see the telemetry coming in at the top of the screen that the visualization tool is using to recalculate the position of this mechanism. And it's a little hard to see with the black background with the black tubes, but you can, if you look carefully at the top, you can start to see the mechanism start to unfold.
this is tremendously exciting to me. So, as this observatory is on its way to its resting point a million miles away, this huge secondary mirror configuration is now deploying, and I can see that the bars are changing on our observatory visualization tool, which is based on real live data from the observatory, and the secondary mirror is deploying. This procedure will take about 11 minutes. About 10 minutes from now, we should see the secondary mirror on our visualization tool fully deployed. The last few days have seen some of the most dramatic deployments from the Webb Observatory. Yesterday, of course, the spectacular finale of deploying the giant heat shield. And today, the secondary mirror. And as you can see, the secondary mirror is now moving away from the primary mirror. I understand it's a little bit dark in the animation, sort of black bars on the black background, but we can see the movement. We can see that this is beginning.
So the mechanism that's actually lifting and rotating this into position is at the top of the mirror there. Is where the motor is located that actually does the deployment. And we have a photograph on the screen of our mission operation manager, Carl Starr. He's up in the top camera shot. As you can see, it's a bright sunny day in Baltimore, which makes it a little hard to see people in the room, in the flight control room in the top box there. But it's great to have good weather while we're doing this.
Carl Starr is you'll hear the acronym, the MOM, the Mission Operations Manager. And you are looking at live coverage of the deployment of the secondary mirror.
Lead on ops with the status. We're about halfway through the deployment. Currents are looking really good, lower than we saw in the ground testing, and everything's looking nominal. So we've got about 5 or 6 more minutes to get to the hard stops.
Oh, right at that. Thank you for the update.
There's a nice view on our observatory visualization tool. So you see this giant boom taking the secondary mirror, the focusing mechanism for the James Webb Space Telescope. The primary mirror are those gold segments that you see. There are 18 gold segments. And after we have confirmation that the mirror has been deployed, we'll have some time to look at how those will be focused. That will be another major commissioning activity for the James Webb Space Telescope in the next weeks. This is the largest and most sensitive space observatory ever flown. It had to be actually folded up to fit inside a rocket. This is something that is historic. We have not done this before, where things need to be unfolded to this extent. So this is very dramatic. There are people all over the world so happy that things so far are going well and wishing for a successful deployment. I know that I have friends of mine who've worked on the Webb telescope since about 1995. So this is many, many decades of people's work and life all happening right in front of you live as we watch that secondary mirror deploy.
And some of the things that are unique about this is the operation of these joints in space and at such a cold temperature. We do have a few heaters that we warm up the motors and some of the mechanism components. But for the most part, the joints have to work in the cold environment of space, which takes special design and special coatings. And as you can see, they also are quite close to our mirrors, so we have to be careful about contamination. This is also the first time to do this deployment in zero gravity. Every other time that we've done the deployment in a clean room, we've had to have gravity considerations. So this is the first time doing it in zero gravity.
We were talking about that yesterday with the non-explosive actuators, all of these little pins that need to release to unfold different parts of the telescope. And again, those were all tested on the Earth, where you were not in zero gravity. They needed to work in space. And Julie, I don't know about you, but every time I see that mirror move a little bit farther in our visualization tool, I'm getting more and more excited. My heart is starting to beat faster and faster. For me, there's a tremendous amount of joy. I mean, I have this smile like on my face from ear to ear right now, as I see this absolutely essential component of the James Webb Observatory, the secondary mirror, the focusing mechanism deployed.
Yes, without this mirror in its right position, we do not get light into the telescope.
And all of those actuators, all of those pins that needed to release in order to unfold this. Julie, can you give me an idea? I believe are there over 300 of those?
Yeah, there's different kinds and different types around. So it's kind of, every time you'll read something, it will tell you a slightly different number, but it all depends on what category they count them in. And for this, what we watched today, there was 3 different ones that we released. So there's so much of that now behind us. There was a lot of work over the years to make sure that these devices worked, and then all the different configurations that we needed them in and the different sizes to make sure that they all worked and they all worked reliably. They're very much like a parachute. They're very sensitive to how they're wrapped and how they're handled. You get one chance to do it right, and if you test it and it works, that doesn't mean that you've done the next one right. So you have to package each one just perfectly. And we're coming very close to being fully deployed. As you can see, the top of the mechanism, the 2 bars there, coming closer and closer to their final position of being in line with each other. And you can, from this orientation, you can now see that the mirror side of the secondary has the gold coating on it too in the visualization tool.
Well, the Webb Observatory is a very large mirror. It's a tiny amount of gold. I believe it's just a couple gold rings worth of gold across the whole thing, just a couple 100 atoms thick on the surfaces. Yeah. Gold was chosen because it is wonderfully reflective in the infrared. This is a heat-sensitive telescope, infrared light, and also gold is very stable and doesn't, unlike something like silver, doesn't react chemically very much. So it's a very good thing to use when nobody can go out there to clean your mirrors. It's all on its own.
So as the mechanism continues to unfold here, the motor will drive it into a hard stop. And from that, then they will start working on the latching procedure.
So we will first wait for confirmation that the mirror is fully deployed. And then after that, as they go through the latching procedure, we'll have some time to talk to our host a bit about the testing and the building of the secondary mirror. We already have a lot of questions coming in through social media. We should have time to get to some of them. But if you'd like to have your question answered, just go to hashtag #AskNASA.
And we have deployed into the hard stops. So we'll move into capturing the latches and then recentering.
All right, as you heard, that went completely into the hard stop. And they'll take a little bit of time to take a look at their telemetry, put the motor into a standby mode, and then move into the latching sequences.
So Julie, at this point, the mirror...
Motor at this point, I'm sorry, I misspoke. They will actually keep the tension on the motor at this point while they do the latching.
So as they are starting latching, I think at this point the mirror mechanism has been fully deployed. Is that correct, Julie?
Yep, the mechanism is fully deployed. The motor is holding it to the hard stop while they do the latching.
I have confirmed with Step Lead that we are ready to proceed with the ADU latch moves. At this time, we are going to proceed onto step 044 to enable SCS 256.
Copy that. That is on the window.
And OC, that looks good. You are go to execute.
Copy executing.
And you heard the term ADU. That's the motor that drives the actuator.
And OC, you are go to enable activate SCS 256.
Copy go to enable and activate 256.
So thank you again for joining us. You're looking at the live coverage of the commissioning of the James Webb Space Telescope. Today, the main task is deploying and now latching the secondary mirror assembly. And that is absolutely essential for the telescope to operate and to be able to focus light onto its gigantic primary mirror. And over on the left side of the screen, you're seeing a visualization produced by real-time data from the telescope. And then above us, you see live footage from the mission control, the MOC, the Mission Operations Center in the Johns Hopkins University.
And OC, verify proc complete, and 256 is enabled and activated in slot 2.
Copy.
The latching that's going to come up.
And OC, I have confirmed with Step Lead that we are ready to perform the first latch off stow move. So at this time, we're going to proceed onto step 046, stow, latch off stow 1 of 3.
Copy that.
And OC, that looks good. You are go to execute.
Roger, executing.
And OC, you are go to continue.
Copy go to continue.
The latches on this that they're discussing now is a hook latch, kind of like you would have on possibly a bathroom door that is, but obviously very highly specialized for this operation. And the deployment motor, the actuator motor, will come in and put that latch on top of a hard stop, and then the motor will pull down to put a preload into the structure, and then the deployment motor will release its push on against the hard stop.
So as we look at the live coverage of this event, we are going to occasionally stop conversation to listen to comments from the MOC, the Mission Operations Center. But as we are now awaiting the latch procedure, which will take about 45 minutes, we're told, we have a time to look at some of the actual instrumentation as it was built and tested at Goddard Space Flight Center. So I believe we're going to be looking at some footage of the delivery of the secondary mirror support structure. And here we have the secondary mirror. Julie, can you tell us what we're looking at in this footage we have?
Sure. So as you can kind of see here, that silver stainless piece is a cover, and then the mirror itself is on a dolly with wheels. And we have engineers and technicians in what we call lovingly as bunny suits in a clean room, and this is, I believe, at Goddard Space Flight Center, doing the initial inspection as they open up the shipping container of the mirror. And now here it looks like we have the mirror up onto the crane and the mechanism to move it up into position where we're going to then do the installation. And here's the people at Goddard watching from the observatory area as the whole assembly takes place. And this is the structure that we were just seeing deployed. You can see it kind of across the middle of your screen, the big booms. And this kind of gives you a perspective of how large in diameter those booms are. You know, they're quite substantial. They look so small in relative to the telescope. But here you can see as we as we deploy it. Here we do it in a horizontal orientation, and they're white there because they have some plastic protective coatings on it, kind of like you would get something shipped in the mail. It's wrapped in plastic bubble wrap. Oh, somebody's got their hand on the camera. There we go. And so you saw two pictures of, or actually 3 different videos of it being deployed. One was as it was being assembled at Goddard in the clean room, and that one was done in a vertical orientation. And then the other 2 tests were done in a horizontal orientation. The one that was done in a vertical orientation, you could see from the top of the picture, and it's a little goes by quickly, but you can see we did some gravity offloading, and then in the horizontal orientation, the gravity offloading was a little different. But testing it in the different orientations is a big part of how we account for gravity effects.
This is Sophie. Go ahead.
This motor move has completed successfully, and DevLead has confirmed we are go to proceed with the latch 2 safe, move 2 of 3.
Copies on the window.
And OC, that looks good. You are go to execute.
Roger, executing.
And OC, you are go to continue.
Copy, go to continue.
And actually, we had a question from Darren on Twitter that asked if the secondary mirror was coated with gold, the same as the primary mirror. And yes, they both are coated with gold because of that wonderful reflective property in the infrared. So, Julie, one of the things that's going on right now is latching. So, now that the secondary mirror has been fully extended, they're latching it into place. I believe we have an animation about the latching and what's going on right now. So, if there we go. You could maybe talk to this animation.
Sure. So you can see that the bottom 2 booms are fixed, and the top one has a joint in the center, and that latch is right there at that center joint. And as you come in close, they don't have the details of the latch itself. It's kind of buried in that structure, but right in there, there's a hook latch that comes over to essentially a hard stop, and then it can pull on that hard stop, almost like a tie down type of latch.
Go to continue with motor move.
And we were talking a bit about testing. Oh, sorry, we were talking a bit about testing and how this has to now function in 0 gravity, when before we were looking at footage of it being tested on Earth. And actually, we even had a question from somebody called Pocket Moon on Twitter. It says, how much do the engineers have to account for operating 0G versus 1G? What were some of the things that during the testing that, how is it that you had confidence this works in 0 gravity when we can only test it in gravity?
Well, the nice thing about gravity is it's in one orientation. So if you want to account for it, you can kind of do things in multiple orientations and take the average and figure out how to subtract it out. So as you can see here, we did tests in different directions. We did testing to the left, we did testing to the right, we did testing upright, and we can figure out exactly what's happening and exactly how gravity impacts us, and take that into account. Same thing with thermal. There's a lot of thermal impacts. We want to make sure that we're testing it, as you can see right there in the clean room, but in space we're going to be much, much colder. So we want to make sure that that mirror is in the right position when we were both in 0 gravity and cold. So we did a lot of measurements both at ambient and cryogenic temperatures to make sure that when we account for both of those effects together, that we wind up in the right spot.
And that's a really amazing thing to think about, that this telescope's operating temperature is nearly 400 degrees below 0 Fahrenheit. And so, I'm sure that, people are familiar a little in their daily life that objects change properties when they are very cold or very warm. So the mirror itself is actually not the correct curvature, each mirror segment, until we come down to the operating temperature of the telescope. So this is something that from the very moment it was designed, we knew that building it and testing it on Earth, we had to be very careful to make sure that everything worked in its real environment in space. And Julie, we actually have some footage, I believe, we can talk about the light path and why the secondary mirror is important. So as we said, this is absolutely essential, the extension of this focusing mirror. So I believe we have some animation. If you could talk to this, Julie.
Yeah, so here you can see like a rather large beam of light coming in from space. It hits the primary mirror, reflects off of that. The primary mirror is concave, and it reflects back. And if you run that again, you'll see that the beam is shaped and reflect back to the secondary, which is convex, and then pushes it down through the center of the telescope here. And that is called our aft optics. And it looks like a little nose in the middle of the telescope. And it actually has a couple more optical features in it. It has a mask that you can see that the light crisscrosses right as it goes through that mask. And then it has a mirror in the back that you can kind of almost see a re-image of what the telescope pupil looks like on that. The pupil is the outside of the telescope. And our telescope is a tricontagon shaped when it's the wings are fully deployed. And that mirror has that same pattern on it. And then it comes back and it hits a tertiary mirror, which then reflects it backwards into the cameras that live behind the telescope itself.
And so this is the important thing. The instrument package is all behind the primary mirror, and this will allow the light to actually go into the telescope. Yes.
Yes. So, just like your telescope on the ground, there's essentially somehow to capture the light. Since we don't go up there and look through the telescope ourselves, we need to have cameras behind the telescope, which take all the images for us. So it would be unfortunate to have like this entire telescope and just have one camera available. So what happens behind that is the light beam gets distributed between the 4 different instruments. So each instrument gets a portion of that beam and then uses their own internal optics to shape and control that beam and filter that beam in different ways before it hits the detector of those instruments, which then the science data comes down to you. Oh, and here's one of our instruments, and you can kind of see that it's on some spindly legs. The stuff that's putting itself out to the right and the left is the legs, and here's the beam of light that comes in and is folded into the instrument, and then it is folded again, and then once again it's folded. This is our near spec, and then it comes through a wall, and it's into the optics and into the camera into the back. You can see the filter wheel spinning there. Actually, I'm not sure that this is near spec.
These are different instruments that are in the ISIM, the instrument package. Some of the most
I don't actually
sensitive
usually
cameras
see
made.
Yes.
Yes.
This is MIRI. Okay. Which is very similar in its 4 optics there. Apologies, MIRI.
We actually have a very good question from Sally Sparks on Twitter, who asks, how are the steps verified? We've been listening to the mock today, the Mission Operations Center, and they say, so this is verified, the engines are on. How are we getting that information?
So we get telemetry. What we have on the telescope is a whole series of sensors of different kinds. We have sensors that are position sensors. We have sensors that are current sensors. We have sensors that are temperature sensors. And all that telemetry gets fed in through the computers and then brought down through the communication system into a ground station, gets sent over to our operations center here in Baltimore, and it comes out on our computer screens. And if you remember looking at the mock, a lot of those screens you have 4 screens there, and there's all different information. Each of those engineers are looking at a different aspect of what's going on. So they'll each have different pieces of information and telemetry coming up that they're checking out. And they can take a look at that, and they can look at the status and the telemetry coming back to get those verifications.
So for our audience joining us, you're looking at live coverage of the deployment of the secondary mirror of the James Webb Space Telescope. This is a second day of very dramatic and successful deployments. Yesterday saw the full installation of the giant heat shield, and today we have the focusing mechanism, the secondary mirror. The secondary mirror has been fully deployed, and at this point they are now latching it. So we actually have a question from Manuel on Twitter that says, why is Webb built to see in specific and longer wavelengths than Hubble? And why didn't you mount shorter wavelength lenses like UV, X-rays, etc.? So this might give me a little chance to talk about some of the science behind Webb and also why it's an infrared observatory. So to answer the question, different wavelengths of light require very different observatories. There basically is no way to build one telescope that can capture all the wavelengths of light. And you see here that infrared light is the color of light that is a bit redder than our eyes detect. You see that there is an area of this, what we call the electromagnetic spectrum. The electromagnetic spectrum is simply a name for all of the different forms that light takes. And our eyes are only sensitive to a very small range of that, which we call, rather obviously, visible light. There are higher energy forms of light that are basically too blue, too high energy, UV light, gamma rays, and X-rays. And NASA does operate telescopes that see in all these different wavelengths, but you need very, very different kinds of instruments and different kinds of mirrors. For example, we have the Chandra X-ray Observatory up right now that sees in X-rays. X-rays are a very high energy type of light. And as you sort of know, colloquially from doctor's offices, X-rays go right through your body, and X-rays, of course, would go right through most detectors and mirrors. You need very specialized detectors. Infrared light is lower energy light, and we often experience this as humans as a form of heat light, infrared light, infrared radiation. The reason we sort of associated it with heat is that objects that are the temperature of a human body, and the temperature, for example, of a planet like Earth, they naturally glow in these lower energy types of light. So the sun is so hot, the surface temperature of the sun about 10,000 degrees, it's hot enough to actually glow, and that produces visible light. But objects that are just warm, really have any temperature at all, they are glowing in infrared light. And we've had many successful infrared telescopes. The Hubble Space Telescope did see a little bit into the infrared, and we see here an image taken by Hubble in visible light of the famous Pillars of Creation. These are dust clouds that are many hundreds of billions of miles across, and they are forming new stars and solar systems inside them. And you see here the optical light, but if we switch to infrared light, Hubble had an instrument called NICMOS that saw a little bit into the infrared. These are both actual images, these are both real data, but this infrared image is one that our eyes do not see. The information has been translated into colors that we can actually interpret and we make this image with. But all of those stars that you see in this image were really there in the visible light image, just not visible in the kind of light that our eye sees. Infrared light has the ability to pass through dust and a lot of obscuring material. And there are some really fascinating things that happen inside these giant dust clouds. So we mentioned the formation of stars and planets. And this is one of the most active regions of star formation in our part of the galaxy. This is the Orion Nebula. The Orion Nebula is actually visible as a faint smudge below the belt of Orion in what we call the sword of Orion. There are sort of three stars that hang down from the belt of Orion. This is the middle quote-unquote star. It's not a star, actually. It's a collection of many hundreds of young stars and planetary systems that are forming inside a vast cloud of dust and gas. And while we can see inside the nebula a little bit where the Orion Nebula is visible to us, it's a much larger complex. And we can see through that dust using infrared. We mentioned the MIRI instrument and also spectroscopes. This is one of the things that's a very powerful way to analyze light. So what a spectroscope does, a spectrograph, I should say, is actually pass light through a prism and break it up into the components of the rainbow, all the different colors of the rainbow. Now, we can actually tell really exciting things from measuring very, very carefully how much color comes from each, how much light comes in each color of the rainbow. That's called spectroscopy. And spectroscopy allows you to do things like discover what the components are made of. And here we see a beam of white light again. And it's being passed through, in this case, a prism. On a telescope, it's usually a grating that does the same thing. It spreads it out into a rainbow, and the graph shows you how much light is coming in different colors. Wherever you see this kind of squiggly line go down, that means less light in that color. The reason that's interesting is that every chemical in the universe, basically, every atom, every molecule, has a fingerprint of light that specific molecule absorbs. And that's how we're able to tell you what stars are made of, what planets that are around other stars, what the composition of their atmospheres may be. This is one of the big deals about the Webb Observatory. One of the major goals is to see, do planets around other stars have environments like the Earth with water vapor, carbon dioxide, oxygen? And the way Webb is going to determine that is by watching that planet move in front of the star, and the star light behind it will pass through the atmosphere of that planet. And as that does, different components will be absorbed because we know the absorption characteristics of all of these different chemicals like oxygen, like water vapor. And as that light reaches the James Webb Space Telescope, we'll be able to say, all right, there's a planet going around that star in the sky that has an atmosphere very much like the Earth. And these are some of the signals that we're looking for. Another reason infrared is so important is that some of the most important signals of this absorption take place in the infrared. If you'd like to know, for example, if there's water vapor, if there's oxygen, not only that, we should be able to have some idea of the temperature of the atmosphere and maybe the density of the atmosphere. And so the hope is that once Webb is operational and looking at exoplanets, planets around other stars, we'll be able to say that planet has an atmosphere very much like the Earth. And perhaps might even have biomarkers, the signals of vegetation. That's less likely. The first thing we'll be looking for is just to find atmospheres that are like the Earth. These are animations, scientific visualizations made of exoplanets. Of course, exoplanets are so far away, we can't yet see whether they have oceans or atmospheres. But these are based on scientific data around a star called TRAPPIST-1. TRAPPIST-1 is a star that we're looking at with the James Webb Space Telescope. TRAPPIST-1 we now know has at least 7 planets. And of those 7 Earth-sized planets that were detected, there are several of them that are about the right distance from the star to have temperatures similar to the Earth. And that's all we know right now is we know the rough size of these planets. We know that they're dense. They are rocky planets like the Earth and Mars and Venus in our inner solar system, but we do not have any information yet about what their atmospheres are like. And hopefully that will change when the Webb telescope is able to send us back information about these exoplanets. That's one of the major science goals of the Webb telescope. You see here some of the exoplanets, again, imagined by our scientific visualizers. We don't have this data yet, but hopefully in the next decades we'll be able to tell you a little bit about. This is the TRAPPIST system, TRAPPIST-1. The way that we find exoplanets is by watching planets transit in front of their sun. They block out a little bit of the starlight, basically a tiny little solar eclipse as these planets move in front. And as the planets move in front with the James Webb Space Telescope, we should also have the opportunity to watch the background starlight of their parent star shine through their atmospheres. And when that happens during a transit, Webb will have the power to analyze the chemistry, possibly the temperature and the density of these atmospheres, and determine whether any of these planets have atmospheres that are friendly to light. And that's what you see here in this diagram. You see an exoplanet in this animation moving in front of its star according to our field of view. And different layers of the atmosphere will actually absorb different things, different wavelengths of light in the infrared. And so we'll be able to actually explore what the environments of these planets are like, even from this far away. Right. Well, let's go back to the Mission Operations Center. Let's find out what's going on.
All stations, this is Mom on Ops. All stations, this is Mom on Ops. As we look at this telescope, I'm going to listen to the PM right now. All stations, listen to the PM.
Thank you, Carl. Hey, I just want to take a moment to congratulate everyone. Another banner day for JWST. In particular, the secondary mirror deployment folks. You guys did a heck of a job. This is unbelievable. We are now at a point where I looked up before, we're about 600,000 miles from Earth, and we actually have a telescope. So congratulations to everybody.
All right. So that was Bill Oakes, our program manager. Congratulating everyone on the operations loop.
You're seeing some high fives there.
And what they've done while we were off talking about exoplanets is they confirmed that the latch had latched and took off the tension from the deployment motor. They will continue to do a little bit to make sure that it's perfectly aligned.
OC, dep ops on ops.
But this is a major deployment and it is locked into place.
This is tremendously
This is
important.
OC, go ahead.
So at this time, we are ready to proceed whenever you are.
Copy that.
Quickly, they have to stop celebrating and continue to work.
That is on the window. Please concur.
DevOps copies. OC, we are going to proceed with step 053 to command the DU to stand by. And that looks good. You are go to execute.
Copy. Executing.
And OC, you are go to continue.
Copy. Go to continue.
So you'll hear us talking. You'll occasionally hear us pause as we listen to commentary from the Mission Operations Center. So Julie, I mean, after today's wonderful and successful deployment of this secondary mirror, a little bit of a look ahead to what's happening next. And tomorrow, I believe we have another significant deployment. The aft radiator will deploy. Can you tell us a little bit about that?
Sure. I think, here's our animation. So this is on the back side of the telescope, actually behind the instruments. And you can see right there on the one side of the screen was actually the mirrors deploying out of the way. But this is a radiator that takes some heat from the electronics and all the different things that still have to operate on the cold side of the telescope and directs that heat out into deep space to dump that power out where it doesn't reflect around and get back into the telescope.
These instruments are designed to operate at very cold temperatures. And after that, we actually now have the deployment of the wings of the main mirror. So what will be happening in the next few days, as you see here, is that the two sides of the mirror had to be folded up to fit inside the rocket. This is the largest space observatory ever built. It had to be folded up to fit inside a rocket. We are now deploying it. And I believe we have footage of the test of the mirrors in the clean room where it was assembled. So if we have that footage to run, Julie, you could maybe comment on what's going on here.
Well, this is back to the secondary deployment that we're doing here. Again, the secondary deployment in a different gravity orientation. And then one last time, in different views, you can see the mirror. Here's the wing coming out. And as you see this, you can see that there's like a black, we call it the frill around the outside of the mirrors. It's kind of like an Elizabethan collar. And what that does is it actually prevents starlight from behind the telescope from passing close to the telescope and actually hitting the secondary mirror and working its way into the optics itself. So that's actually soft structure. It's a blanket-like material made out of kapton. That's a real low reflectivity, and it keeps the light from poking its head around the backside of the mirrors and making its way in. And here you can see a technician or an engineer taking a close look as we close to make sure everything's happening just perfectly. And behind that, you can see people on things we call diving boards. We had to do a lot of work high up in the sky the telescope is so big, you couldn't be standing on the ground and doing the work on it. So our technicians got good at being up high on cranes and on diving boards, we call them. And you could see that they had fall protection to make sure that they didn't fall. Their tools had to be tethered to make sure they didn't drop anything. It's
that the SAP load has completed successfully. So at this time, we are going to proceed on to step 055 to command the DE to operations mode, frame 14.
For us here in the clean room,
and OC, that looks good. You are go to execute.
Copy. Executing.
And
we have to wear masks because of COVID, but that's nothing compared to working in those suits all day in the clean room. So, so my kudos to all the people who worked so hard all that time to put it together. We shouldn't complain at all wearing our COVID masks.
Right. Well, so to wrap up today's broadcast, we have had live coverage of the successful deployment of the secondary mirror, the focusing structure of the James Webb Space Telescope. This is an absolutely essential component of the observatory, and I am smiling, and I was very excited to see this happen. Joining me has been Julie Van Camp. She is the Deputy Commissioning Engineer. and also the main system engineer for the instrument package. A very historic day. So this particular observatory will take about 29 days to fully deploy. After that, it will cool down, and we will actually have to wait a few months for the first images because of cooling down. But so far, everything has gone absolutely wonderfully.
And OC, that input looks good. You are go to execute.
Copy that. Executing.
And OC, you are go to continue.
Copy, go to continue.
And OC, stand by for verification.
Copy, standing by.
And OC, DepOps on ops. Those parameters look good.
We
are go to move the SMSS
lost
motor.
audio.
Copy, go to move.
Okay.
Motor status goes moving.
It's all about flames, fluids, and materials research aboard the International Space Station. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life.
Houston 2 for velocity confirmation assembly. It's 45 and 46. We're moving on to
Tracy, you want to go right now for that activity?
Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.